This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Good afternoon. So today we will start a PCB design. That is because you will be soon submitting your Gerber files for fabrication. So maybe it's a good idea to discuss about the PCB design in general. Why do we need a PCB? And then some routing rules, different grounds. Why do you need different grounds? So these concepts we will be discussing under PCB design, which is very important for an electronics engineer, because PCB design, without designing PCB, you can't make a system. But when you design PCB, then you have to keep in mind the main thing. Maybe what I would learn from this one is, obviously PCB you can learn from Altium, because that is a more practical way of doing. But then when you are routing your PCB, you have to always think of how current flows, because most of the time what we are so far, if you have designed so many systems, then you may have experience. Otherwise, when you are routing, definitely you will make mistake, especially high frequency boards, if you don't know how current is flowing. So you have to keep in mind not voltage, but current, how the current is flowing. That is an important part when you design a PCB. Second thing is, many of you think that ground plane is stationary. like a ground plane, nothing is happening. That is just a ground. Actually, ground plane is not stationary. Current is returning. That is a return path. It is not same as VCC, but current is flowing in the opposite direction to the source. So ground plane is not something like a neutral one or a static current. No, ground plane is active plane. Current is flowing through the ground plane. So these are some two important concepts you have to learn. First is when you are routing your PCB, think of how current flows. Second one is when you put ground planes, you have to keep in mind that ground plane is not static. Ground plane means the return path of the current. So PCB design, so we will start from basic. So what is a printed circuit board? Because that is a expansion for the abbreviation of PCB, printed circuit board. So copper, we use copper plated fiberglass or other non-conductive material. Holes drilled for components. So you can see in the PCB, the holes are drilled for components when you are using through-hole components, but through-hole components are not very popular these days. In your case, you will be using surface mount and maybe one or two through-hole, maybe capacitors. But in high-frequency boards, you will find no through-holes are used because of the parasitic inductance and capacitance. We will be using surface mount. Then copper removed to create wires or tracks. See, you can see here the tracks are created here using copper. Then why use a PCB? So this is maybe an example of some of your DSO design. Printed circuit board, see, so it will be neat. If you got a PCB, everything will be neat. Easier to assemble, neater, more robust. Because if you make a system like this, definitely there will be problem with the shorting, and then when you may put it in a box, many wires will come off and your system will not work. Why do you use a PCB? Sorry, when do you use a PCB? So when you use a PCB, after you are sure of your design, breadboard first if possible. So some circuits you can't do breadboarding, especially high frequency one. And even if it is not high frequency, if you don't have the through-hole components, through-hole means with the leg. If you got a surface mount IC, how can you breadboard it? Because some people try to connect wire to the surface mount and then breadboard it. Yeah, in low frequencies, maybe it will work, but I wouldn't recommend that. You can't do that one. So after you are sure of your design, so that is the reason you will be designing your PCB after submitting the front end design. So at least you know that up to front end it will work. So that's the reason we are making sure that your design is correct. And when using surface mount components, see, when do you use a PCB? If you got surface mount components, no way of breadboarding, you can't check it, so you need PCB. So different types of PCBs. So PCBs you will see two layers. Most of the time you will see only two layers these days. One top surface and then bottom you see ground, something like that. But in the past, people have used single-sided, means all the connections are on one plane. Now also some people make a single-sided in some high-frequency designs, but mostly you will be seeing two-sided. Your DSO is a double-sided, means you will have, this is a FR4. FR4 is the dielectric material used for making PCBs at low frequency. So you might have seen only, I wouldn't say only, mostly FR4 boards, FR4. So that is the material, dielectric material. On the top, we will be depositing copper for the track and making footprint. Again, we got ground plane. So this is a FR4 material, and then this is single-sided. Only one side you have got a copper, and here you will be mounting the components. Double-sided means you got copper on the top and the bottom. Bottom might be ground. You can mostly use it as a ground, and then here you have all the connection signals. And when you are using a high-frequency boards operating at say 2 gigahertz or above 1 gigahertz, then we will not be using FR4. FR4 means then you are pushing the boundaries of the FR4. So for example, if you are designing a 2.54 gigahertz bandwidth or the frequency 2.54, because that is a number, standard number, and 2.54 gigahertz means you will be using Rogers board. It's called a Rogers. That's a special type of dielectric board that will not attenuate high frequency signal. Rogers board. But in your DSO, definitely we don't need a Rogers board, we need only FR4. Then multi-layer. Sometimes you will see multi-layer. See, this is how many layers? One. So how many? This is how many layers? Yep. So this one got 4 layers, and so multi-layers. So these days you will see multi-layer board. So advantage of multi-layer is then you can have so many connections even in between. You can have plus VCC, minus VCC, and maybe in the in between layers, so that your PCB will be really compact. So that's the reason people use multi-layer board. Has copper on both sides as well as layers of copper in the middle. So this layer could be, sometimes it's a ground, and then this could be plus VCC, so maybe minus VEE. So then the different ways you can design multi-layer board. Even some people route signal in the middle line, but then low frequency, because high frequency it is not a good idea to route the signal in the middle layer of a multi-layer board, because then you will be putting vias or vias. You will be putting vias and then signal that is not good for high frequency lines. How do you connect to different layers? So when you make a multi-layer PCB, vias are small holes to permit a connection from one layer to the other layer. Because when you have multi-layer, but then you have to connect together the layers, because this layer should be connecting to this layer, then we will be using vias. Vias are made by either wire or through-hole plating. So you will see through-hole plating when you see the via in the PCB, that is made through-hole plating. Then also they have got some reliefs. So that is called reliefs. Easier to solder through hole components. Through-hole components. When you have through-hole components, we use reliefs. Reliefs means you will see design like this. See, this is absence of copper. Then here absence of copper. The white part is absence of copper. And then here you got small copper fingers connect barrel to the plane. See, here one connection, here one connection, here one connection, and then maybe this is a ground or a power plane. Higher inductance to the ground plane. So if you make connection like this, so this is a copper plane, so this could be ground or power plane, and then this is a component that you are soldering, so that when you put the component here, when you put solder, it is connecting to here. Via should be directly connected. Anyway, these things you have seen a PCB. So layer stack legend. So when you are in an industry, so industry people will ask you, when you are designing a multi-layer board, you have to write clearly how many layers are there, and then in each layer, is it a ground plane or a signal plane or a power plane? You have to write it clearly. So this is kind of an industry way of looking at your 10-layer construction detail. So in the industry, they will be drawing something like this. And then silk screen. So silk screen is a color that you see. Then you got solder mask. Then this is a bottom ground. So you have to write it correctly. And then how much copper? 0.5 ounce copper. And so all these details will be written when you are in an industry, when you are designing a board. So layers of a PCB are constructed as signal or plane layers. These layers must be clearly documented when there are more than 2 layers. So different types of PCBs. So as I said, so here 4 layer, 1, 2, 3, 4 layers. So this is a signal. So here signal, routing and components. Here you will be placing your components. Below, then you will be having a ground plane. Then below you have a power plane plus VCC. Then here you have lower speed signals. So this is a 4-layer board. 6-layer board. If you are designing a 6-layer board, this is an example. Your signal routing or components on the top. Then you will be having a ground plane. Then you will be having a signal routing. Usually here this signal, so here if you got a signal, then nobody will put another signal below that one. That is not a good design. They will put a ground plane and then you route the signal. Then power plane. Then again a ground plane. Then again a signal routing. So this is the 8-layer. In the 8-layer you can see signal, ground plane, again signal you can route it, again you can have a ground plane, then you can have a power plane, again you can have signal, again you can have ground plane, again you have signal plane. So the take home message is when you have signals, better to isolate with a ground plane. So that's how in the multi-layer board people do. So ground plane polygons. So this one maybe you might not have seen. In old days you will see PCB. Now you have got a continuous copper. This one is called a hatched or solid. So this one is hatched. There are two types of designs. When you put the copper, when you see the ground plane, you may see solid or hatched. Maybe you haven't seen. Anyone seen hatched plane PCB? Maybe, yeah. Okay, good. Yeah, sometimes what they do is they make a hatched. So this is a hatched one. So this is a solid one. Solid means a continuous copper. Sometimes you see like a net, something like this. So that is hatched, where you will be using less copper. It is less weight. You don't need much copper. It's less weight. Controlled impedance, higher inductance, reduced capacitance, faster heat up time, less efficient thermal relief. Because it's not good when you have heating in the PCB. Solid design is good because this cannot dissipate much power. Obviously, because you don't have much copper to dissipate the power. Higher impedance, better for low speed designs. Then solid PCB, you might have seen, most of you might have seen only the solid design, means your ground plane is solid. Good for high speed designs, lower inductance, lower resistance, larger thermal mass. So what is meant by larger thermal mass? When you have a continuous copper plane, even if your IC is getting heated, the heat will be dissipated on the copper. And then copper got large area, so it can dissipate, so that your IC will not damage that easily. But here it can damage because it doesn't have much copper. The component classes. So this is called through hole components. See, through hole components. Then that will be mounted something like this. Sometimes they use it directly mount through hole components on the PCB. But if it is not very high frequency, the through hole component ICs are not directly mounted. Instead they will use some kind of a holder. See, why? Because when this IC is damaged, then you have to take off these legs and then you have to cut the legs and take off, then you may damage the PCB. But if you put this type of holder, the advantage is you can just take off and then replace it with a new IC. Then that is possible when you have through hole components operating at low frequencies. Obviously high frequency ICs you don't get this through hole. And then you have got a surface mount. See, this is a surface mount IC. So there is no hole, but then we will be mounting on the pad. So in the DSO design you have got a microcontroller, then you have got some other ICs. Those are surface mount. You will find it's a bit difficult to solder it. You have to solder very carefully under a magnifier. So this is also surface mount. Then component classes. Each component type has a footprint, because that you know the footprint, because you are using Altium. In the Altium, when you design circuits, you have to provide a footprint for the IC, which not only defines connection but also signal integrity and properties of the package. See, usually people say SMD. SMD means a surface mount device. So SMD devices often depend on their connection to the PCB for cooling and thermal stability. So these are some kind of SMD, SO1414. So this is a package. SO8. So if you see SO8 means it got 8 legs. See, 1, 2, 3, 4, 5, 6, 7, 8. Something like this. SOT means then you will see something like this. Here you got 3 legs, here you got 2. So that is SOT package. That is 223. SOT23 means is still smaller and difficult to solder it actually, SOT23. So these are the packages. So SOT, SOT223, SO8, SO14. Then these are the ICs. When it comes to resistors or capacitors, capacitors may be C, B, A. These are the names used. So this is a resistor. For the resistor 1206. So some people say my resistor, surface mount resistor I am using is 1206. You might be using 1206. Then when it is in very high frequency like 2.45 gigahertz, people will go for 0805. or 0603. See, very small. So these are used in high frequencies, 0603 at very high frequencies, because this is a small size. When you have small size, your parasitic inductance, parasitic capacitance and parasitic resistance will be small. So that is the reason we are using very small at high frequency, 0603. So I have used 0603 maybe 10 or 12 years ago when we designed a 2.54 gigahertz board. 0603 means these components are not new, these numbers. Then PCB routing. So PCB, when you are routing, the common question is when you check your PCB, see, this is a design, when you have a bend, they always make a 45 degrees. See, here there is a bend. You can see here there is a 45 degree. So nobody will make a 90 degree bend while designing the PCB. When routing signals, trace width should remain constant. Means this width should be same as this width. You should not change the width. Trace should be routed using two 45 degree turns instead of single 90 degree turn. So when you have a bend, usually see one 45 degree, another 45 degree. See, use two 45 degree turns instead of one 90 degree turn. So that is the rule. Trace length should be kept at minimum, as longer traces are more susceptible to electromagnetic interference, and trace inductance and resistance increases as the trace length increases. Means these are applicable in high frequencies. When you have one connection from one IC, it is going to another IC, you have to keep minimum length of the track. Track length should be minimum. Otherwise, what will happen is electromagnetic interference means when something is oscillating, suppose your signal is operating again at 2.54 gigahertz. So what it means is your signal is going, it has, the variation is there, 2.54 gigahertz is going through the track, means a lot of radiations will be coming. Why? Because your signal is oscillating. Because that much variation, 2.54 gigahertz is the variation, signal is going up high, is a clock, maybe it's a clock. Then what is happening is sometimes intensity is very high, it is low, very high, it is low. So gigahertz means the variation is in nanosecond. In nanosecond time, your signal is varying in the track. So that is like what will happen when the charge is oscillating, what will happen? It's kind of a dipole antenna, so that variation can couple. It can emit or it can couple to the next one due to inductance. You may have another track going nearby, then if this track is varying quickly, then it can couple to the other track. So electromagnetic interference. Also, if the length is more, as I said, at high frequencies you have parasitic inductance, parasitic resistance. These are the monsters you will be seeing at very high frequencies. Then the question, so when I was a student, I asked the same question. If I make 90 degrees, what is the problem? So if you make 90 degrees in low frequencies, it is not at all a problem, but that is not professional. Nobody will design 90 degree bend. Then at high frequencies, definitely 90 degree bend is a problem. For example, in high frequencies, the signal behaves very differently. So a 90 degree bend, because some students get confused when somebody is asking, I will make a 90 degree bend, what is the problem? Then you can't say that is a PCB design rule, you can't violate. But you should be able to explain. Then you can say that, okay, 90 degree bend, low frequencies, definitely it is not going to affect. But high frequencies, when you have a 90 degree bend, how the signal is, because 90 degree, so you got this 90 degree bend here. So this is your PCB. See, so if you got a 90 degree bend, if your signal is coming very high frequency, so very high frequency, then the signal will, so this point is maybe T, and then this point is T dash. Then how the signal will see this one as a inductor, capacitor, inductor, something like this. So this is T and then this is T bar. So at high frequencies, the high frequency signal will see the 90 degree bend as something like this. Two inductors and then middle there is a capacitor. So the high frequency signal, then this will create a lot of issues. Inductor, see here, then you got an inductor, then capacitor, again inductor. So that's how high frequency signal sees. So that is a problem. So that's the reason we use 2 45 degrees. not 90 degree, 190 degree. So this will not be used. So our design, whatever we are designing, that is should be equally applicable to high frequencies. So that's the reason we are using 245 degrees. Otherwise in low frequencies, you will not see any effect. But low frequency also we use 245 degrees because that is a standard way of designing. Otherwise maybe somebody will ask you prove it. Low frequency is pretty difficult to prove it. 90 degree also will work it. But then that is not professional. That is not allowed because in high frequencies when you have these type 90 degree bend, it will see as two inductors and a capacitor connected in the middle. And then that will maybe reflect your signal or attenuate your signal, mostly maybe will cause a reflection. High frequency signal will be reflected back. So then if this type 45 degrees will minimize, I will not say fully avoid it, but minimize it. So that's the reason we will be using 245 degrees. Then coupling capacitors. So this coupling capacitor, so the name sometimes people are confused because in different articles people use different names. Some people use coupling capacitors, some people use decoupling, some people use bypass capacitors. So because of the literature, what I did is I read a lot of white papers and then I classified properly. So maybe you can follow my classification so that you won't get confused. So for example, this slide is I taken from a PCB power supply circuit with decoupling, and then I think this is from analog devices if I remember correctly. So anyway, the name is called coupling capacitors. Bulk, so the name is coupling, but then the problem is in there when you read it they will be using coupling and decoupling interchangeably, but then there is a difference. So we will study into that, all these things clearly. So bulk decoupling capacitors should be placed close to the output pin of the voltage regulator. So when you have a voltage regulator, what you have to understand is, don't forget about these names. People usually put a big tantalum electrolytic capacitor. So why we use a tantalum electrolytic capacitor? Because here electrolytic, it got a polarity and you can get very high values. You can't get this big value with the surface mount. So that is the reason tantalum electrolytic. But then you can see here this is a curvature here in the capacitor representation, means this one got a polarity. So here you have to connect positive, this one should be connected to the ground. So usually near the voltage regulator, people connect a tantalum capacitor. Then typically the power supply decoupling capacitance value should be 10 times that of local capacitance of the decoupling capacitors local to each IC. See, they are using decoupling, again here decoupling. Actually it is not correct. It should be bypass. But I am just showing is when you read some of the white papers, they will be using decoupling everywhere. They are using this one as a decoupling, then near the IC is again decoupling. Tantalum or electrolyte capacitors are commonly used for bulk decoupling. So this is what you will be reading, but then the reading, that the names are confusing actually. See, they say that a power supply decoupling capacitance. So this is the power supply decoupling. Value should be 10 times that of total capacitance of the decoupling capacitors local to each IC. Means near the IC also you put some capacitors. In some literature people use that as a bypass, but then here they are again using that as a decoupling. You know what I meant? So we need some kind of distinction, then only this concept can be learned properly. So this is a standard way of connecting a voltage regulator. From here you are getting maybe 5 volt. Then you have got an analog part, then you have got a digital part. So this is a standard way of connecting, means extracting power from a voltage regulator 5 volt. You got only one 5 volt supply, voltage regulator, but from there you have digital ICs and analog ICs. And then this is how you will be connecting. Then before going to that one, we should be understanding the role of capacitor, then what is bypass, what is decoupling, all these concepts. So for that what I did is, so this is my slide. So I categorized this into 3 because in the ECD we studied coupling capacitor. So coupling means you are connecting the amplifier to isolate the DC. So that makes sense. You see coupling capacitor. So coupling capacitor is used to connect 2 circuits such that only the AC signal from the first circuit can pass through the next while DC is blocked. See, only the signal can pass through this capacitor. The DC bias points it will not pass through this capacitor. This technique helps to isolate DC bias settings of the two coupled circuits. So these type things are used for isolation. Then that is called a coupling. So I wouldn't use the term coupling when you have a capacitor near to the IC. So coupling for me it is this one. Then bypass. This makes sense. Bypassing is, this is bypass something. Bypassing is the reduction of high frequency current flow in a high impedance path by shunting that path with a bypass, usually a capacitor. See, near the IC you may generate some noises because of the switching. Then people connect a capacitor near to the IC. You know what I meant? Near to the IC, when you connect a capacitor for bypassing the noise, that is called a bypass. Then decoupling. So decoupling means is the isolation of two circuits on a common line. For example, decoupling capacitors are used when you have digital ground, digital supply and analog supply. So then these things should be clear now. Coupling. So these are the convention I am following, because so that there won't be any confusion. So coupling capacitor means usually, then you have to ask someone, when somebody is talking, you have to make sure that they may use decoupling as bypass. So you have to talk to them where you are connecting. So then you can make up your mind. So coupling means usually coupling capacitors in the amplifier for isolating DC. So bypass means that you are connecting near the IC. So around the IC people connect bypass capacitors. Then decoupling. So when decoupling word is heard, then you should understand there are kind of different part, maybe digital part, analog part, such as. So this is the convention I am following, because otherwise what will happen is in some literature they use decoupling, again they use the name decoupling here. Well, in one way it is correct, but that is not, it's confusing. So these are the, maybe I like this convention. And then I will be sticking on with this convention, and then if you have any questions you can ask me. Then I will go to document camera, because then only we can understand why do we need decoupling or bypass capacitors. So in your PCB, so this is your PCB. So you got a big PCB. So you made a PCB, then you got different ICs, and then you have to power it, and then usually you use a regulator. So why do you use a regulator? Because we don't know, your power supply may be 12 volt, maybe coming in, and then your requirement may be plus 5 volt, minus 5 volt, such as, so that you will be using a regulator IC. Then, so here example I am going to use only one. So here plus 5 volt is getting. Then you have to power your ICs. So when you are powering your IC, this is a IC1, and then this is an amplifier. Then I got IC2. So this is a digital switch. So this is an analog, this is a digital. These are the two ICs. So then what you will do is, we have to connect. Then you might connect like this, common PCB top layer. You are connecting this analog here, then you are connecting the digital IC, and then you have got your ground. Then you have got your ground connected together, and then that ground is connecting here. So this is the ground plane. So when you connect like this, what will happen is, suppose this digital switch is switching at 500 megahertz, and then this amplifier maybe you are using for amplifying very small signals like 2 microvolt or something, and then this is an amplifier circuit. So here, when this IC is switching at 500 megahertz, then you got an amplifier that is operating at 2 microvolt. Then you might think, what is the problem? Definitely there is problem. Why? Because digital IC, so when you look inside, what is happening is, in the digital IC you got a transistor, and then maybe something like this, so many transistors are there, and then maybe here it is operating at 500 megahertz, and then this is connected to plus VCC. Then when you are 500 megahertz means, then this transistor is on and off at 500 megahertz, very high frequency. Then what is happening is, you are drawing the power when this transistor is on, is stopping when the transistor is off. Then what will happen? When you are drawing, not drawing, drawing, not drawing, means then you lot of noise you are generating here. So the digital IC will generate a lot of switching noises. and then that switching noise is due to this switching on and off the transistor. When the transistor is on, the power is drawn, the current is flowing, collector current is flowing. When the transistor is off, the collector current is not flowing. You know what I meant? So that you are at very high frequencies, you are drawing the current, not drawing, depending upon the switching. So that will generate a lot of noise. That noise will go to the power supply, and then this noise can come to your analog IC. Then your analog IC got problem. Then see, this noise is coming here, then it will couple to here, and then another issue. So this is the issue number 1. So the problem number 1 is noise from ICs, especially digital. Then another second issue. So that is one problem, noise from IC, that is on the power line. So that's the reason I have written here power line. See, noise from ICs, especially digital, on the power line. Then second issue means this 500 megahertz you are switching, and then this regulator is near this end of this PCB, and then you got a copper track this length. So when it is a DC, it is fine, but when the signal is changing very fast here, then what will happen is at 200 megahertz or 500 megahertz, then the parasitic inductance will come into picture. So that is here. See, parasitic inductance of the track. So that is this part 2, and then this is the first. See, then you got 2 issues, and then parasitic inductance, even parasitic resistance, even parasitic capacitance. Mainly the inductor is the problem. So that's the reason I have drawn inductance. So parasitic inductance of the track is coming into picture. So when you have parasitic inductance, what will happen? There will be some, whenever there is an inductance, when the current is changing, what will happen? There will be EMF. Then you will have attenuation, you have problems. So then these are the now 2 issues. Then what you will do? So that is the reason we have to isolate analog and digital part. And then so what we will do is we will isolate this analog part, and then we will isolate the digital part. Then you might think that I will not isolate first. Then what I can do is you can connect some bypass capacitors. See, these are called bypass capacitors. Bypass. So when this design IC is made, the manufacturer already tested it, and then they found out that this IC will generate such and such noises. Maybe you can put a 0.01 microfarad, and then maybe you can connect another 0.1 farad or 10 nanofarad. So the manufacturer will say, so these are the bypass. So when you have bypass capacitors, and then this values they recommend. So when you have using IC, they recommend some values near to the IC, around the IC, please put 0.01 or 0.02 nanofarad, they will tell you. So you can put those numbers, and then when you put those numbers, why they are putting that capacitors? Because the inductance, the impedance of the capacitor equal to 1 by 2 pi fc, and then they know when you take a Fourier transform, they know that the major frequency components is this one, and then for that the impedance is lower for this one. So that then what is happening is this noise is not going to this line much. So you can short to the ground, and then you can short to the ground. So then you kind of avoid it. So by using this bypass, so when you use bypass capacitors, short noise to ground or high frequency switching noise. So either noise or high frequency switching noise, you can put a bypass capacitor around it. Even analog also people put it. So then you are putting this to the ground, so that you are grounding all the noises, so that this part is kind of avoided. But still, even though you are putting this much bypass around it, but still this noise is not fully suppressed. Still it can go to your analog part, because analog is very sensitive. Digital means you got only 2 levels, maybe 0.5, that may be your 0, maybe 1.5, maybe that is your 1. So that is you got a noise threshold. So if you got some noise of 200 millivolt in the digital line, is not going to affect it because your 0 is 0.5. But in the analog line is analog signal that will be amplified. Your amplifier, if some noise is coupling, if your amplifier got thousands of gain, this will be amplified in your signal. So even if you are using bypass capacitors, still you have to isolate your analog part and digital part. But this bypass definitely will short some of the noises and then it can make it clean. So then bypass will work only in one scenario. So you got your regulator, then you are getting here, this is a 12 volt ground, and the bypass will work. This is a IC2. So when you have all the digital circuits, so all these are the digital circuit, D, so D. So all digital circuit, then you can connect in one side and then you can put appropriate bypass capacitors. So all the digital circuit you can combine. So this part is called a digital part. So in the digital part, so maybe I'll write properly. So digital part. So in the digital part, the advantage is so you are combining all the digital ICs and then the noise is generating. That noise is not coupling back because a little bit only going this line, but most of the noises are you are coupling to the ground, coupling to the ground, coupling to the ground, coupling to the ground, coupling to the ground. So that you are avoiding noise from the ICs in the power line, means this is a line, active line, so you are shorting the noise to the ground.
Why have to use two?
Sorry?
Why have to use
So actually we use sometimes 3. Why? Because as I said, not 2. Impedance, so that's a good question. Impedance of the capacitor is 1 by 2 pi FC. And then when you are putting this capacitor, you have to make sure that for a particular, because in the noise, if it's a pure noise, this will lead to switching. But switching got some frequency components. Then we will be aiming the major components. We should be shorting. But if it should be shorted, for example, this frequency components will come here. And then it will look for which is the low impedance path for that frequency component. So then if this is not the low frequency one, this will go here or this will come here and it will come here. You know what I meant? So that's the reason these capacitors will be designed in such a way that that particular frequency components go to low impedance path. So when you have multiple, they put 2, 3 actually around the IC, because one will be more favorable to some frequency components. So that's the reason manufacturer recommend. So then this one solved one issue, that is a noise from the power line, and then so we are isolating. So then what we will do is we will put our analog ICs here. So all the analog we will put, and then this IC, all the analog ICs. So that also you will be having bypass capacitors, IC4, IC6, sorry. Yeah, so these are analog ICs. So this is analog part. So analog is grounded. So again analog you got capacitors. So these are the analog ICs. So these are the analog ICs. So then this is part analog isolated. So analog here, then digital here. But then we got one more problem, that is parasitic inductance of the track. Means, as I said, when this is switching at 500 megahertz, then because the current is traveling all the way, then this part is switching on and off, and then this inductance will come into picture at high frequencies. So how will you avoid this one? Straightforward solution. Well, that is a maybe a bit more sophisticated, but straightforward, what will you do? So reduce the track size. But then when you are reducing the track size, your regulator will come and sit closer to the IC. But then that is not possible. You go to many ICs. Then what you can do is, then you can think of some innovative solution. So maybe what you can do is you can connect a big capacitor. Then why need a big capacitor close to these ICs? So that is called a decoupling capacitor. So that this is a polarity. Why? Because when you want a, maybe this one may be a 10 microfarad. When you put this capacitor, the advantage is, what is the advantage? This capacitor will charge it to 5 volt, because this is a big capacitor, it can charge a big value, and then the regulator from here to here, see, this will be charging, and then this IC, when it is switching, the IC will be taking power from this capacitor. You know what I meant? Then this capacitor, the IC is taking power, this IC is taking power, and the ground is finished here. So this is kind of a local power supply. And then this part is not much affected because this part is a DC that is charging only the capacitor. So the high frequency, the return, so the return current, so that's the reason the DC means, see, the current is flowing from here, this capacitor, because 500 megahertz transistor is switching on and off at 500 megahertz. So the current is going, not going, so this is going, and then this is, when the transistor is on, it is coming to the ground plane. From the ground plane, see, the current is returning and then coming to this ground. See, circuit is closed. So that is the reason we put a big capacitor. The capacitor should be big because you need to charge, store the charge, that much charge, and also then this this can short a lot of noises as well. If some noise is even coupling, it will not go to the regulator. Even some noises, it is not shorted by this bypass, it can come to decoupling and to short it. So then the main purpose of decoupling is not shorting the noise, that is secondary. For the bypass capacitor, the preliminary job of the bypass capacitor is shorting the noises, high frequency noises. The primary job of decoupling capacitor is providing a local battery or local cell or local power supply, so that the circuit will be closed here, so that you don't have the inductance problem. Now you got the inductance of this much, it's a small. So it is very important in high frequency designs. Secondary purpose of this one is even if some noise is still coming, it can bypass it. See, because it's a capacitor, so that it is not going to here.
Instead of using so many small bypass, why can't we use just one very large bypass capacitors for entire?
Yeah, so that's a very good question. So his question is, instead of using one big decoupling here, and then we are using so many bypass around the IC. So by his question is, instead of using so many bypass, then we can use a one decoupling with each IC. Definitely that is a very good solution because that can short almost all the noises. It will reduce the length of the track, but the problem is the size. The tantalum capacitors, electrolytic capacitor is so big. So if you got 10 ICs, then you are taking more space, more space.
No sir, I'm saying is why not use a very big capacitor or only two capacitors, one for decoupling and one for complete bypass?
Now one, it is very difficult to get a one value here because this, if you are putting only one, the value should be very high, and then the surface mount you don't get that big value. So this you can get maybe 1 microfarad, 0.1 microfarad, or usually we put nanofarad because that's small, and then also this should be tuned to a particular frequency. And then yes, if you put a bigger value it is good, but then you should put a very big value, not 0.1 microfarad. Then you may have to put a maybe 10 microfarad. 10 microfarad will, the advantage is when you put it, it will also give a power supply. It's active power supply. Also it will short the noises in most of the frequency region, but the problem is then you are increasing the size. Because of the size problem, because this capacitor is so big, we connect like this, and then bypass will work out. And then, so this one we solve the issue. Then if you don't know about the capacitor, why this is good? Even this is even much better than drawing directly from here. Not only because of this track inductance, but still this capacitor will make your circuit very stable. Why? Because when you have a capacitor, see, you got a capacitor here, then you have connected this to a IC, then grounded, and then you got a regulator, and then you are getting 5 volt. So when you have this capacitor, what will happen is this capacitor will be charged to 5 volt. But due to some reason, this 5 volt became 4.999 volt. Some spike came, like the spike was like 5 volt constant, but immediately you got a spike like this that appeared here. Here you will not get that spike. Why? Because the spike will come, but then the capacitor doesn't like change in the voltage. So when this part will come, capacitor will discharge that part here, this point, so that here you will get a smooth line. So the capacitor, because if the capacitor is connected to something, if the voltage is changing, reducing, the capacitor will discharge. and then compensate it. So this type also some spike, the capacitor will discharge it and compensate that spike, and you get a straight line. So that also is good. So that decoupling even can smoothen your power supply. So that is important. Then the problem is, so you got a decoupling here that is applicable to only couple of ICs. Then again you need to connect decoupling. You know what I meant? Still you need a couple of decoupling. So then we solved two issues. One is the noise from the power line. So these are the power lines we bypassed using these bypass capacitances. Then the parallel inductance of the track, parasitic inductance of the track, then we reduced by using a decoupling capacitor. And then we also isolated analog and digital part. So now we got analog part somewhere, and then here we are going to connect a decoupling capacitor. So this is a decoupling, and then this is the analog part. But then when you connect this one, I wouldn't say that this will completely avoid all the noises. It can still, see, this is a decoupling capacitor, so maybe I can connect this to here. So that here you are getting 5 volt, and so at the moment your circuit is closing here. The current is going and then it's passing through this one, then it's a ground, and then return is here. So this is your power supply for the ICs, local power supply. Same with analog. But then this you got a digital part you will be putting here, analog part you will be putting here, then you got a common ground. So in the common ground, but still we are not foolproof. Why? Because some noises are coming, it will be shorted, some noises will come here, it will be shorted through this capacitor, and then some noises will come, it will be shorted through this this capacitor, but still you are taking from there to the analog, but still you may have a little bit noise. It's not a foolproof. So in order to make even much better, people put a ferrite bead, an inductor here. So that is called a ferrite bead. So it's basically an inductor. So if you put an inductor there, it's called a ferrite bead. So what will do? So what is the difference between capacitor and inductor? So capacitor doesn't like change in the voltage. Inductor doesn't like change in current. So inductor, if you check inductor, what is it? So capacitor dV by dt. So that is a capacitor, but then inductor means di by dt. So you can remember. So this is a change in current. So when there is a lot of noises, then what will happen? The inductor will not pass through. Inductor doesn't. But if it is a DC, inductor will be short. If it is a DC current, inductor will be short. But if you got some noises, inductor will block it. Then it's just opposite of capacitor. If you got some variation, capacitor will bypass, because capacitor block DC and pass through the AC, the noise, some variation. Inductor short DC, acting just opposite of capacitor, and then the noises, variations, it will block it. So then if you put a ferrite bead here, very good design, so that the noises comes even it is not coupling to this side. If you put a ferrite bead here, even better. See, you got two double protection. Here also, then analog part is completely isolated. So that is the reason in the design, when you come back to the slide, so this design is a very good one. See, here you have got a voltage regulator. Now you can make sense. Here you got a big tantalum electrolytic capacitor. That is your local power source. So that this part, even though that is here we have drawn small, but this could be big, because this regulator will be in one end of the PCB, so that we don't have the problem with the parasitic inductance here, this track, because this is acting as a local capacitor, decoupling capacitor. Then this is for the analog. So here this analog also, they again connected one more tantalum if you want to make it maybe again good. And then these are some capacitors for again bypassing the noise, and then this is your analog, maybe plus 5 volt. Then here they are using a ferrite bead or inductor, so that the noise, even because this is connecting to the ICs, so even if some noises is coming, you got the bypass capacitors here with ICs, but still some noises can come, so this will bypass to the ground. So this also can connect to the ground. This also can act as a local power supply for the analog ICs. Even some noises is coming here, the ferrite bead will block it, so it will not come here. Then you got digital supply. See, So digital also you are connecting from here. So for the digital supply, this is a local source, means you are connecting to IC1 here. That IC1 will be switching, that power is taken from this tantalum electrolytic capacitor and the circuit is closed here. You know what I meant? So your digital ICs are working here in this domain. Current is going from this capacitor and then going through the IC, the ground is coming here and closing here. So digital, this is doing, and then digital and analog isolated with a ferrite bead. And then in order to avoid the track length issue, again you are